When the $10 billion device trained its infrared vision on the exoplanet K218b, 120 light-years away, it detected dimethyl sulfide, a sulfur compound that, on Earth, is produced exclusively by organisms. Does this mean that the matter is settled? Can we finally answer the oldest question of mankind, whether we are really alone in the universe, with a clear no? Well, that is precisely the crux of the astronomical debate. While one side of the experts is already popping the champagne corks, the other side is calling for a little more patience and pointing out that even the capabilities of the most powerful space telescope of all time are limited. Hand on heart, in most people's daily lives, dimethyl sulfide, or DMS for short, probably plays no significant role. In fact, most people have probably never even heard of this particular chemical compound, even though they have likely encountered it at one time or another. In detail, DMS is formed by microscopic algae, the phytoplankton, which drift in the uppermost layers of the ocean, and it's responsible for the typical smell we notice when we are at the beach. Apart from its sniffing properties, DMS also has another important characteristic. So far, we only know of biological sources for this sulfur compound, and where the production of a substance requires the help of organisms, it's understandable that DMS plays a very special role in the search for extraterrestrial life. It's even more understandable when considering the cries of joy that came from the lips of the Cambridge astronomers in September 2023. After all, the James Webb Telescope had detected nothing less than this potential biosignature on the exoplanet K218b. The overwhelmed discoverer, Niku Matuson, then told the press that he and his colleagues were completely shocked by their readings. No wonder, because, after all, the existence of DMS in the vastness of space is nothing less than a serious indication of extraterrestrial life. What initially came as a shock to the experts soon developed into almost euphoric reporting, which unceremoniously elevated the James Webb Telescope to the key to the cosmic search for life. But is the matter really as clear-cut as it seems? If the corresponding molecule on Earth is only produced by living things, and we then discover it on an alien body, why hasn't NASA officially announced that our microscopic neighbors are slumbering on K218b? Well, that's because, as so often, the devil is in the details. But basically, the conditions in the case of K218b are anything but bad. This water world, a haven for life located about 120 light-years from us in the constellation Leo, is under the exciting suspicion of being a water-world planet. In other words, a planet whose surface is completely covered with water and can therefore support life. And while K218b was added to the star charts in 2015 with the help of the Kepler Space Telescope, it orbits its central star, the red dwarf K218, within the habitable zone. This, in turn, describes the distance range at which a planet must be located in relation to its host star for water to be able to exist there in a permanently liquid form. As we all know, the cool, wet element is considered one of the fundamental pillars for the development of life, similar to that on Earth. And although K218b is significantly cooler than the Sun, its planetary companion receives roughly the same radiation as our Earth due to the given constellation. The bottom line is that K218b is only 0.14 astronomical units away from its parent star, so it takes just 33 days for a complete orbit. Indeed, the pro column on this life discussion list also contains the entries methane and carbon dioxide, two further indicators that suggest we may actually be dealing with a habitable planet here. If this is really the case, it would be a cosmic novelty, because so far, these exotic water worlds only exist on paper. But while the detected large amounts of methane and carbon dioxide, in combination with the lack of ammonia, suggests that K218b is a Neptune-like planet
Nick
covered by
Boza
liquid
is a
water.
name that has rapidly
The
become
detected
synonymous.
substances also present an unfortunate complication. They make it all the more difficult to interpret the DMS data correctly. The mystery of the biosignature, in principle, the DMS signal was anything but pronounced in the collected datasets, and it only revealed itself when the data was analyzed in a very specific way. The matter was not made any less complicated by the fact that the DMS signature identified by Webb's near-infrared spectrometer, NIRSpec, appeared in a spectral line at a wavelength of 3.4 micrometers, thus overlapping with the methane. And that's precisely the crux of the matter, because the scientists believe that distinguishing between DMS and methane is simply beyond the capabilities of NIRSpec. But does this also mean that Webb's capabilities have already been fully exhausted and that we will not be able to uncover the true background to the DMS question? Well, fortunately not. The researchers also emphasize that unequivocal proof is possible in principle. After all, DMS and its breakdown products also generate a signature in the mid-infrared range, between 9 and 13 micrometers, and conveniently, this is exactly the range in which Webb's MIRI spectrometer works. While the first NASA announcements still spoke of a possible detection of the molecule dimethyl sulfide, in this context, the Cambridge scientists finally wanted to know more. And so it happened that the astronomers once again used Webb's sharp infrared vision to get to the bottom of the mystery surrounding the supposed biosignature. In the course of this, the experts allowed 8 hours for the targeted search for DMS. 1 to 2 days later, the research team should receive the data and begin with the evaluation. However, it's in the nature of things that such data evaluation, to say the least, is laborious. In other words, it takes months before it's fully completed. The good news, however, is that the experts have already been working on the analysis for half a year, and it can therefore not take much longer before the latest findings of the presence of DMS on K218b are published. When we can detect the DMS, fortunately, the rest of the astronomical world is not condemned to just waiting and twiddling their thumbs in the meantime. After all, they can also approach the DMS question from a theoretical point of view. In other words, with the help of their models, scientists are able to check when we will be able to detect the existence of DMS on K218b. And that is exactly what the team led by Shang Minai of the University of California in Riverside has now done in detail. The researchers reconstructed K218b and its possible biochemistry using several models simulating the planet covering ocean and atmosphere. The scientists then had to test how much DMS our extraterrestrial micro-neighbors would have to produce for it to accumulate in the atmosphere in a way that we could detect, and how quickly it would be broken down again due to radiation. The study concluded with the exciting result that the current data evaluation by the colleagues is not in vain, because, theoretically, it's possible that biogenic sulfur gases on hydrogen-rich ocean worlds like K218b could accumulate to detectable concentrations. And yet, as so often, the big but follows at this point. Because this only applies if the organisms of K218b are real workhorses. In fact, the extraterrestrial DMS production would have to exceed that on Earth by a factor of 20 for us to be able to register it with our instruments. This is for the simple reason that most of the DMS is broken down again immediately by photochemical decomposition due to solar radiation. In the case of significantly higher concentrations, which are quite conceivable for hypothetical ocean planets, a natural protective effect would arise that would put a stop to the DMS loss. Accordingly, its degradation products, such as dimethyl sulfide and methane ethyl, form a kind of protective shield around the lower atmospheric regions, which are thus protected from further DMS degradation. However, only the future will tell to what extent this scenario corresponds to reality. What is already clear, however, is that the unequivocal confirmation of DMS would be no less than an unprecedented milestone in the history of space exploration. And while the team at Cambridge is currently busy evaluating the new datasets, as mentioned above, the lead scientist emphasizes that even one direct detection would be enough to revolutionize the entire history of science. No wonder, after all, humanity has been pondering for millennia whether there are other life forms out there, and ultimately just a single example would be enough to end the millennia of speculation in one fell swoop. Whether the extraterrestrial life breakthrough will be named K2-18b cannot be said with absolute certainty at this point, and yet we currently know of no other candidate that opens up such a promising lead for us in our search for life in space. And the trail of your video search now leads you straight to the subscription button. Feel free to click the thumbs up and subscribe so you never miss a new video from us again. We'll see you soon.